For billions of years, asteroids have crossed the inner solar system in silence, ancient fragments left behind from the birth of the planets themselves. Most will never come near Earth. Some already have. From the impact that ended the age of dinosaurs to the explosion over Chelyabinsk in 2013, these objects have repeatedly reminded Earth that the solar system is still active and still unpredictable. Tonight we'll explore what asteroids are, where they come from, how scientists track potentially dangerous objects across space, and the extraordinary systems humanity has built to detect and possibly deflect a future impact before it happens. Before we begin, let me know in the comments below where you're tuning from and what sleep science topic you'd like to hear about next. Now let's begin, one calm fact at a time. Asteroids are rocky, airless remnants left over from the formation of the solar system approximately 4.6 billion years ago. That age places them among the oldest solid material in the solar system, substantially older than Earth's continents, older than the oceans, older by orders of magnitude than any biological organism. For context, the entirety of recorded human history spans roughly 5,000 years. The period during which non-avian dinosaurs inhabited Earth covers approximately 165 million years. The asteroids formed during the same process that produced the planets, from the same rotating disk of gas and dust that surrounded the young sun, but unlike the material that accumulated into the terrestrial and gas giant planets, asteroid material was never fully drawn together into a single large body. It remained fragmented, distributed across the inner solar system and concentrated in a broad band between Mars and Jupiter, shaped by the competing gravitational influences of the planets around it. Meteorites recovered on Earth's surface, including thousands of specimens systematically collected from the Antarctic ice sheets, are direct physical samples of this population. When subjected to isotopic analysis and radiometric dating in the laboratory, these rocks yield ages of approximately 4.56 billion years, consistent with the age of the solar system itself. They are older than the planet whose surface they rest on. Most asteroids are composed of rock and metal, with some containing carbon-rich material and trace amounts of water ice. This compositional diversity reflects the range of formation conditions in the early solar system and the different histories individual objects have experienced over the billions of years since. Silicate-rich asteroids, the S-type classification, are common in the inner belt and share their dominant mineralogy with the terrestrial planets. Metallic asteroids, composed primarily of iron and nickel, are thought to be the cause of larger parent bodies that melted and differentiated early in solar system history and were subsequently shattered by collisions. The most scientifically significant category for both solar system science and the question of life's origins is the carbonaceous or C-type asteroids. Dark, primitive bodies found primarily in the outer belt, relatively unchanged since the early solar system, that contain complex organic molecules, clay minerals holding chemically bound water and amino acids, the same molecular building blocks used by all known living organisms. Direct analysis of returned samples from carbonaceous asteroids, from Japan's Hayabusa 2 mission to asteroid Ryugu and NASA's OSIRIS-REx mission to asteroid Bennu, has confirmed the presence of amino acids, sugars, and a range of organic compounds in concentrations and varieties that bear on the question of how organic chemistry first became established on the early Earth. The word asteroid derives from the Greek asteroides, meaning star-like, because early telescopes showed these objects as faint, unresolved points of light indistinguishable in appearance from stars. What distinguished them was motion. Stars, at their vast distances, appear fixed in position relative to one another when observed over days or weeks. Asteroids, orbiting the Sun at far shorter distances and measurable speeds, shift detectably against the stellar background between images taken on successive nights. This technique, comparing photographs of the same sky region taken on different nights and identifying points of light that have changed position, remains the primary method of asteroid discovery today, though the instruments and computational infrastructure supporting it have changed entirely. In the early 19th century, a single observer might spend weeks tracking a newly noticed moving light with a refracting telescope. Today, automated survey systems photograph tens of thousands of square degrees of sky each clear night, and software algorithms scan the resulting images in near real time, flagging candidate moving objects for human review or for automated follow-up observation. The underlying logic, find what moves, measure how it moves, compute where it is going, is unchanged. The scale and speed of the operation are categorically different. Asteroids range in size from a few meters across to approximately 525 kilometers in diameter for Vesta, the second largest object in the main belt. Vesta is large enough to have undergone internal differentiation, its interior separated into a crust, mantle, and iron core, and its surface preserves a complex geological history, including a large impact basin at its south pole, whose formation very nearly disrupted the entire body. At the opposite extreme, objects a few meters across are numerous but faint, and the great majority have not been individually catalogued. Between these extremes, the size range most relevant to planetary defense spans roughly 25 to several hundred meters, objects large enough to cause significant regional or global damage if they were to strike Earth, but small enough to have largely escaped systematic detection until recent survey improvements began finding them in increasing numbers. Size correlates with nearly every other relevant physical property: rotation rate, surface structure, mass, internal composition, and orbital response to non-gravitational forces. No two asteroids are exactly alike. The variation within the near-Earth population is sufficient that any specific potentially threatening object requires individual characterization rather than assessment by analogy to a generic model. Unlike planets, asteroids lack sufficient mass to pull themselves into spherical shapes through self-gravity. Gravity rounds large bodies by pulling material toward a common center from all directions, a process that occurs when the self-gravity of a body exceeds the compressive strength of its constituent material. Most asteroids fall well below this threshold. The result is that their shapes reflect their formation and collision history, elongated, angular, bilobed, or irregular in ways that no planet could maintain. Spacecraft images of asteroids visited at close range, Ida, Eros, Itokawa, Ryugu, Bennu, Dimorphos, have shown surfaces that bear no resemblance to smooth, spherical bodies. They are heavily cratered, strewn with boulders, and shaped by the cumulative record of billions of years of collisions. This irregularity is relevant to planetary defense planning for several reasons. An elongated or bilobed asteroid rotates differently from a compact one, and the distribution of mass within it affects how it responds to a kinetic impact or a gravitational tug. A heavily cratered surface with loose regolith may absorb or redirect impact energy differently than a cohesive surface. Characterizing an asteroid's shape and surface properties is therefore not merely scientifically interesting, it is engineering relevant information for any mission designed to alter its course. Many asteroids are not solid monolithic bodies but rather rubble piles, loose aggregates of fragments held together only by weak mutual gravity. This structural model emerged from spacecraft observations and radar measurements that found many asteroids to have bulk densities substantially lower than the density of the rock types they appear to be made of, implying large interior voids consistent with a loosely packed aggregate rather than a solid mass. A rubble pile asteroid is, in physical terms, a gravitationally bound collection of rock and dust, the result of a collision that broke apart a larger precursor body, with the debris slowly reaccumulating into a new aggregate under the pull of its own gravity. The distinction between a solid rock and a rubble pile has direct implications for deflection planning. A kinetic impactor striking a solid body transfers momentum in a predictable way, and the resulting velocity change can be calculated from the impactor's mass and velocity using standard mechanics. The same impactor striking a rubble pile may partially bury itself in loose surface material, excavate a large ejector plume, or trigger a restructuring of the internal fragment arrangement, all of which affect the efficiency and direction of momentum transfer in ways that require specific modeling. DART's target, Dimorphos, is believed to be a rubble pile, and the results of that mission are being analyzed in part to quantify how rubble pile structure affects the kinetic impactor's performance. Some asteroids have their own moons. In 1993, the Galileo spacecraft discovered that asteroid Ida had a small companion body orbiting it, subsequently named Dactyl. Dactyl is approximately 1.4 kilometers in diameter and orbits Ida at a distance of roughly 90 kilometers. The discovery was unexpected. Prior to Galileo's Ida flyby, no one had confirmed that asteroids could host natural satellites. Since that first discovery, subsequent observation has established that binary asteroid systems, pairs of objects in mutual orbit, are relatively common. Studies of the near-Earth population suggest that roughly 15% of near-Earth asteroids are binaries. Several formation mechanisms have been proposed with the Yorp thermal effect, a process that gradually spins up certain asteroids until centrifugal force causes material to be shed from the equator, considered among the most likely for the smaller near-Earth binaries. The DART mission targeted one such binary system. Didymos, the primary, is approximately 780 meters in diameter. Dimorphos, the moonlet, is approximately 160 meters in diameter and orbits Didymos at a distance of about 1.2 kilometers. The binary configuration was a primary reason for selecting this system as the deflection test target, because a change in Dimorphos's orbital period around Didymos, directly caused by the spacecraft impact, could be measured precisely from Earth using standard photometric techniques. Asteroids produce no light of their own. They are visible only because they reflect sunlight, and the fraction of incident sunlight reflected, a property called albedo, varies substantially across the population. Dark, carbonaceous asteroids reflect as little as 3% of incident sunlight. Brighter silicate and metallic types can reflect up to 50%. This variation has a direct practical consequence for asteroid detection. A dark asteroid reflects far less light toward a ground-based telescope than a bright asteroid of the same size at the same distance, making dark objects substantially harder to detect. Ground-based optical surveys are therefore biased toward higher albedo asteroids and the dark carbonaceous population, which represents a significant fraction of the total near-Earth asteroid inventory, is correspondingly underrepresented in survey catalogues relative to its true abundance. Space-based infrared telescopes address this limitation by detecting thermal emission rather than reflected light. All asteroids, regardless of surface brightness, absorb solar radiation and re-emit it as infrared energy, and an infrared instrument detects this emission with comparable efficiency across the full albedo range. This is one of the primary technical justifications for the NEO Surveyor space-based mission. Infrared detection from space provides a survey that is far less biased by albedo than ground-based optical detection, and it accesses approach directions that ground-based telescopes cannot monitor due to solar interference. The surface temperature of an asteroid in the inner solar system typically ranges from approximately -73 degrees Celsius on its shadowed side to roughly 27 degrees Celsius on the sunlit side, with the exact values depending on the asteroid's distance from the Sun and rotation rate. This temperature differential produces a subtle but physically significant effect on the asteroid's orbit. When sunlight is absorbed by one face of a rotating asteroid and subsequently re-emitted as infrared radiation, the slight asymmetry in the direction of that re-emission, caused by the time delay between absorption and emission as the asteroid rotates, creates a tiny but persistent recoil force on the body. This phenomenon is called the Yarkovsky effect, and while the force it produces is extremely small for any given asteroid, it accumulates over years and decades into an orbital drift that can reach thousands of kilometers per century for small to medium-sized objects. The Yarkovsky drift was first detected directly on a near-Earth asteroid in 2003 and has since been measured for several hundred objects. Its relevance to planetary defense is practical as well as scientific. Accurate, long-term predictions of an asteroid's orbital position require knowledge of its Yarkovsky drift rate, which in turn requires knowing its size, rotation state, and thermal properties. Without this information, impact probability assessments for encounters decades in the future carry larger uncertainties than the gravitational orbital solution alone would suggest. Meteorites recovered on Earth's surface, including thousands of specimens collected from the Antarctic ice sheets, are pieces of asteroids that survived passage through the atmosphere and reached the ground. Antarctica is a productive collection site because the cold, dry conditions preserve meteorites from weathering, and the slow movement of ice sheets concentrates specimens in specific areas where they can be systematically collected. The contrast between dark meteorites and white ice also makes specimens visually easy to identify. Laboratory analysis of these samples has produced detailed information about the composition and early history of the solar system. Among the most scientifically significant findings from meteorite analysis has been the identification of pre-solar grains, microscopic particles that formed in other stellar systems before the Sun existed and were incorporated into the material from which the solar system formed. These grains are identifiable by their isotopic compositions, which differ distinctly from the isotopic signatures of material that formed within our own solar system. They are the oldest solid material ever directly analyzed in a laboratory, billions of years older than the solar system itself. Their presence in meteorites demonstrates that the rocky material composing asteroids, the planets, and ultimately the crust and mantle of Earth was assembled from the output of multiple generations of stars that lived and died before the Sun was born. The majority of asteroids in the solar system are located in the main asteroid belt, a region between the orbits of Mars and Jupiter, approximately 2.2 to 3.2 astronomical units from the Sun. 1 astronomical unit, the average Earth-Sun distance, is approximately 150 million kilometers, placing the inner edge of the belt at roughly 330 million kilometers from the Sun and the outer edge at approximately 480 million kilometers. The belt is a broad, diffuse ring of material orbiting the Sun in the same direction as the planets and occupying the zone where, under different conditions, a rocky planet might have formed. Its total mass, however, is far less than any of the terrestrial planets, estimated at only about 4% of the Moon's mass, indicating that the zone never accumulated significant material, rather than that a planet formed there and was subsequently destroyed. Despite containing millions of individual objects, the belt is not densely packed in any physical sense. The average separation between objects large enough to be individually tracked is several 100,000 kilometers, and every spacecraft that has traversed the belt has done so without requiring special navigation to avoid collisions. The visual impression of a dense asteroid field, common in science fiction, has no basis in the actual spatial distribution of objects. The main asteroid belt is estimated to contain between 1.1 and 1.9 million asteroids larger than 1 kilometer in diameter, along with a vastly larger population of smaller objects. A 1-kilometer asteroid striking Earth would release sufficient energy to trigger global climate effects, placing it at the lower boundary of the size range capable of causing civilization-scale consequences. Despite the large number of kilometer-scale belt objects, the total mass of all material in the belt is modest, approximately 4% of the Moon's mass, because the overwhelming majority of individual objects are small, and even the aggregated mass of the millions of sub-kilometer bodies contributes relatively little to the total. The mass budget is dominated by the handful of largest objects. Ceres alone accounts for roughly 1/3 of the entire belt's mass, and the 4 largest bodies combined hold more than half the total. This mass distribution is consistent with a population that has been grinding down through collisions over 4.6 billion years, with larger bodies continuously fragmenting into smaller ones while the total mass remains approximately constant. The belt observed today is substantially less massive than the early belt was, and the grinding down process continues at a slow rate today. Jupiter's gravitational field is the primary reason the material in the asteroid belt never consolidated into a planet. Jupiter is the most massive body in the solar system after the Sun, more than twice as massive as all other planets combined. And its gravitational influence reaches across hundreds of millions of kilometers with enough force to continuously disrupt the orbital behavior of belt objects. Rather than allowing collisions between belt objects to gradually build up progressively larger bodies, Jupiter's repeated gravitational perturbations inject orbital energy into the belt, increasing the relative velocities at which objects collide. Higher collision velocities favor fragmentation over accretion. Objects hitting each other at high speed are more likely to break apart than to stick together and grow. The result is a population in a state of ongoing collisional equilibrium rather than growth. This equilibrium has persisted for the full history of the solar system, and the asteroid belt today is the product of 4.6 billion years of this process, far less massive than it was in the early solar system when the grinding had just begun. Jupiter is therefore not simply a neighbor to the belt. It is the principal agent that has determined the belt's character and maintained its current state throughout the history of the solar system. Within the main asteroid belt, several distinct empty zones known as Kirkwood gaps appear at orbital distances where an asteroid's orbital period would be a simple fraction of Jupiter's, ratios of 3:1, 5:2, and 2:1, among others. At these resonance distances, Jupiter's gravitational influence is periodically reinforced in the same orbital direction rather than averaging out over time, because the asteroid always reaches a particular point in its orbit at the same moment in Jupiter's orbital cycle. The result is a cumulative, unidirectional gravitational kick that increases the asteroid's orbital eccentricity over millions of years, eventually elongating the orbit enough that it crosses Mars's path. Mars's gravity then provides additional perturbations that can redirect the asteroid further toward the inner solar system, placing it on a trajectory that may carry it into near-Earth space. The Kirkwood gaps are therefore not simply empty regions. They are the gravitational conduits through which the near-Earth asteroid population is continuously replenished, as objects drifting into resonance zones are gradually redirected inward over timescales of millions to tens of millions of years. Without Jupiter's continuous perturbations feeding new material through the Kirkwood gaps, the near-Earth asteroid population would diminish over time as objects are removed through impacts, gravitational ejection, or orbital decay. Jupiter maintains the supply. Trojan asteroids are populations of small bodies that share a planet's orbit around the Sun, residing at the gravitational equilibrium points known as Lagrange points L4 and L5, located 60 degrees ahead of and behind the planet in its orbital path. At these positions, the combined gravitational influence of the Sun and the planet creates stable zones where smaller objects can remain indefinitely without requiring thrust or energy input to maintain their position. Jupiter has by far the largest confirmed Trojan population, with hundreds of thousands of catalogued objects divided into a leading group 60 degrees ahead of Jupiter and a trailing group 60 degrees behind. NASA's Lucy mission, launched in October 2021, is the first spacecraft designed to study Jupiter's Trojan asteroids at close range. Over its 12-year mission, Lucy will fly past multiple Trojan objects in both groups, returning detailed images and spectral characterizations of bodies that have remained largely undisturbed since the early solar system. Because Jupiter's Trojans formed in the outer solar system, where temperatures were lower and the abundance of volatile rich material was higher, their composition is expected to differ from that of the inner belt asteroids that dominate most survey catalogues. Information from the Lucy mission is expected to provide new data about the conditions and composition of the outer solar system during the period of planetary formation. Jupiter is not the only planet with associated Trojan asteroids. Mars, Neptune, and Earth have all been confirmed to host small Trojan populations at their respective Lagrange points. Earth's sole confirmed Trojan, designated 2010 TK7 and discovered in 2010, is approximately 300 meters in diameter and occupies the L4 Lagrange point 60 degrees ahead of Earth in its orbit. Computer simulations of 2010 TK7's long-term orbital behavior indicate that its position at the Lagrange point is not perfectly stable over very long timescales, and the object is expected to drift out of the Trojan zone over millions of years. Neptune's Trojan population is thought by some models to be comparable in total number to Jupiter's, though the great distance and faintness of these objects makes comprehensive survey difficult with current instruments. The existence of Trojan populations around multiple planets reflects the universality of the Lagrange equilibrium geometry. Wherever two gravitating bodies are in orbit around a common center, the L4 and L5 points exist, and wherever those points are stable over the relevant timescale, material tends to accumulate. The solar system has many more instances of this configuration than observation of the major planets alone would suggest. Near-Earth asteroids, abbreviated NEAs, are defined as asteroids whose orbits bring them within 1.3 astronomical units of the Sun, a threshold that places their orbital paths within the region of the inner solar system where Earth's orbit is located. The designation does not imply that any given near-Earth asteroid poses an impact risk. The vast majority have orbits that carry them past Earth at distances that preclude any encounter, and the full computation of their trajectories confirms no plausible impact scenario within any foreseeable time frame. The 1.3 astronomical unit threshold is an orbital geometry definition. Objects within this range have paths that overlap with the inner solar system zone where the terrestrial planets move, as distinct from objects whose orbits remain confined to the main belt and beyond. Within the broader near-Earth population, a subset receives particular attention: those whose orbits pass within a defined proximity of Earth's path and whose size exceeds the threshold associated with significant damage potential. These objects receive more frequent observation, more detailed orbital characterization, and regular reassessment of their impact probability as new data becomes available. The broader NEA population is also scientifically valuable in its own right. These are the closest solar system objects to Earth, the most accessible to spacecraft missions, and among the best candidates for studying the original material of the early solar system in physical detail. Near-Earth asteroids are subdivided into 4 orbital families: Asteroids, Atenes, Apollos, and Amors, each defined by the geometry of the object's orbit relative to Earth's. Asteroids have orbits lying entirely within Earth's orbit, placing them always between Earth and the Sun, and making them extremely difficult to detect from ground-based observatories due to their proximity to solar glare. Atenes have orbits mostly interior to Earth's, but crossing it at their outermost extent. Apollos have orbits that cross Earth's orbital path from the outside, carrying them both interior to and exterior to Earth's orbital distance. Amors approach but do not quite cross Earth's orbit. The Apollos and Atenes represent the populations of primary concern for near-term impact risk, since their orbits geometrically intersect Earth's. Amors are monitored because gravitational perturbations can gradually shift their orbits into Earth-crossing territory over time. These classifications are not fixed permanently for any given object. Over millions of years, orbital evolution driven by planetary gravity and the Yarkovsky thermal effect can move an asteroid from one category to another, meaning that the current classification of a given object describes its present orbital geometry rather than its permanent character. Near-Earth asteroids are not primordial inhabitants of the inner solar system. They originated in the main belt and migrated inward over millions of years through a combination of gravitational perturbations and the Yarkovsky thermal effect. The migration process is gradual and cumulative. An asteroid drifting near a Kirkwood Gap resonance zone experiences repeated gravitational perturbations from Jupiter that progressively increase its orbital eccentricity over tens of millions of years. As the orbit becomes more elongated, it eventually crosses Mars's path, and Mars's gravity provides additional perturbations that push the orbit further into the inner solar system. The Yarkovsky drift contributes by slowly shifting the asteroid's semi-major axis until it enters a resonance zone capable of accelerating the inward migration. The entire sequence, from a stable main belt orbit to near-Earth classification, takes tens to hundreds of millions of years. Because objects are continuously being added to near-Earth space through this process at the same time that others are being removed, through impacts with planets, gravitational ejection from the solar system, or orbital decay into the Sun, the near-Earth asteroid population maintains an approximately steady-state inventory on geological timescales. The specific objects that make up the near-Earth population today are not the same objects that occupied near-Earth space 50 or 100 million years ago. A small fraction of near-Earth asteroids are believed to be extinct comets, formerly active cometary bodies that exhausted their volatile inventory through repeated close passes near the Sun and now circulate as dark, inactive objects compositionally and geometrically similar to rocky asteroids. Active comets are defined by the presence of gas and dust coma produced when solar heating vaporizes subsurface ices during perihelion passage. Each pass near the Sun depletes a portion of the volatile inventory. Over sufficient numbers of orbits, the ice is exhausted, and the body loses its cometary activity. The remaining nucleus, dark, rocky, inert, continues in its orbit but produces no detectable coma or tail. These objects occupy a compositional intermediate between typical rocky asteroids and active comets, and they are of interest to planetary defense for a specific reason. They may retain the highly elliptical orbital characteristics of their cometary precursors, including long orbital periods and approach trajectories that emerge from the outer solar system with limited advance warning. Unlike main-belt asteroids that migrate inward gradually over millions of years and can be detected by surveys as they approach the inner solar system, an extinct comet on a long-period orbit may present itself with significantly less warning time before a potential encounter. As of 2024, NASA tracks more than 35,000 near-Earth asteroids, with the total increasing steadily as survey capabilities improve. Each catalogued object has been observed on multiple occasions, had its positional motion measured across successive images, and had an orbital solution computed from those measurements. That orbital solution allows scientists to calculate the object's past and future positions over extended periods, in many cases decades to centuries. The rate of new discoveries has grown substantially since the 1990s, driven by improvements in telescope aperture, detector technology, and the automated image processing software that can analyze thousands of images per night for moving objects. In the early 1990s, only a few hundred near-Earth asteroids were known. By 2000, the catalogue had grown to roughly 1,000. By 2010, the population of kilometre-scale and larger objects had been substantially inventoried. The catalogue continues to grow, with the most rapid progress now being made in the detection of smaller and fainter objects. The current total of more than 35,000 represents a nearly complete accounting of the largest and most dangerous objects in the near-Earth population, combined with an expanding but still incomplete survey of the smaller, more numerous objects that current instruments are only beginning to fully characterize. Among the more than 35,000 known near-Earth asteroids, more than 2,300 have been classified as potentially hazardous asteroids, a technical designation applied to objects meeting two specific criteria. First, the object must be estimated at more than approximately 140 meters in diameter, the threshold above which an impact would be expected to produce regional rather than purely local damage. Second, the object's orbit must pass within 0.05 astronomical units of Earth's orbital path, approximately 7.5 million kilometers. Both criteria must be met for the PHA classification to apply. The designation does not indicate that any specific object is currently on a collision course with Earth. It indicates that the object is large enough and moves in orbital proximity close enough to Earth's path that its long-term trajectory requires sustained monitoring. The majority of PHAs, when their orbits are fully characterized with sufficient observations, show no credible impact probability within any foreseeable time frame. A small number at any given time carry non-zero impact probabilities that are being refined through continued observation. The PHA catalogue is updated continuously as new observations accumulate and existing orbital solutions are improved. The 140-meter size threshold for potentially hazardous asteroid classification reflects the energy scale at which an impact transitions from causing primarily local damage to causing regional destruction with broader humanitarian consequences. An asteroid of this diameter striking land would release energy equivalent to several hundred megatons of TNT, comparable to a large nuclear weapon in yield, and would devastate an area measured in thousands of square kilometers through blast overpressure, thermal radiation, and ejecta. An impact in shallow coastal water would generate tsunamis capable of inundating coastlines across a wide region. The 0.05 astronomical unit orbital proximity threshold reflects the practical limits of long-term orbital prediction. An object whose computed trajectory passes within this distance of Earth's orbital path may, with improved measurements or accounting for small perturbations not yet included in the model, be found to have a closer or intersecting approach than the current solution shows. The two thresholds together identify the subset of near-Earth asteroids that combine meaningful damage potential with meaningful orbital proximity. Objects that warrant active, ongoing monitoring rather than a single characterization and no further attention. Scientists estimate that approximately 1,000 near-Earth asteroids larger than 1 kilometer in diameter exist, and surveys completed over the past 3 decades have identified more than 95% of this population. None of the known kilometer-scale near-Earth asteroids is on an impact trajectory within any foreseeable timeframe. This level of survey completion represents the fulfillment of the SpaceGuard goal established by Congress in the early 1990s, which directed NASA to find and catalogue 90% of near-Earth objects larger than 1 kilometer within 10 years, a goal substantially achieved by approximately 2010. The significance of this accomplishment for planetary defense is direct. For the class of asteroids capable of causing global climate disruption and threatening civilization, humanity now has a nearly complete inventory, and that inventory contains no impending threat. The remaining few percent of undiscovered kilometer-scale objects represents the residual uncertainty in this assessment. Continued monitoring of already known kilometer-scale asteroids is also necessary, as their orbital solutions require periodic updating to account for the slow accumulation of Yarkovsky drift and gravitational perturbations that shift predicted positions over long timescales. The known population of large asteroids is not a static list but an actively maintained catalogue. Near-Earth asteroids smaller than 140 meters are far less completely surveyed than the larger population. Scientists estimate that tens of thousands of such objects exist in near-Earth space, with only a small fraction currently discovered and catalogued. This gap is a recognized limitation of current planetary defense capability. Objects in the 25 to 140 meter size range are too small to cause global catastrophe but large enough to cause significant regional destruction if they were to impact in a populated area. The Chelyabinsk event of 2013, involving an object estimated at approximately 20 meters in diameter, caused injuries to roughly 1,500 people from shattered glass across a wide area, and that object arrived entirely undetected. A 50-meter object striking an urban center could cause casualties and property damage on a scale comparable to a large conventional weapon. The challenge in surveying this population is sensitivity. Objects of this size reflect far less light than larger ones, and detecting them at the distances that would provide years of warning requires instruments substantially more capable than those that sufficed for the kilometer-scale survey. Closing this gap is the stated priority of the NEO Surveyor space-based mission, which will observe in infrared wavelengths from a position that allows it to detect both dark and bright objects and to survey orbital directions inaccessible to ground-based telescopes. The total mass of all material in the main asteroid belt is estimated at approximately 4% of the Moon's mass, a figure that effectively rules out the hypothesis that the belt is the remnant of a destroyed planet. A rocky planet comparable to Earth or Mars would be hundreds of times more massive than the current belt. The low total mass indicates instead that the belt represents original solar system material that was never able to accumulate into a planet because Jupiter's gravitational perturbations continuously disrupted the accretion process. The mass distribution within the belt is heavily concentrated in its largest members. Ceres alone holds roughly 1/3 of the total belt mass, and the four largest bodies, Ceres, Vesta, Pallas, and Hygeia, account for more than half the total. The millions of smaller objects that make up the remainder contribute a comparatively small fraction. This distribution is what one would expect from a population that has been losing mass through collision-driven fragmentation and slow grinding over billions of years. The total mass decreases gradually as material is lost from the belt through various ejection mechanisms, and the size distribution at the small end continues to increase as larger objects break apart. The asteroid belt is not a stable configuration. It is a slowly evolving system that has been losing material since the solar system formed. New near-Earth asteroids are discovered at a rate of roughly 2,000 to 3,000 per year, reflecting sustained improvements in survey telescope sensitivity and sky coverage. Each new discovery follows a standard processing sequence: identification of a candidate moving object in survey images, follow-up observation on subsequent nights to confirm the motion and establish an initial orbital arc, submission of the measurement data to the minor planet center, computation of an initial orbital solution, and assessment of whether the new object poses any impact risk. For most discoveries, this sequence confirms quickly that the object is non-threatening and its orbit is unremarkable. For a fraction each year, the initial orbital uncertainty is large enough to include possible Earth-intersecting trajectories, and those objects receive immediate intensive follow-up observation to resolve the uncertainty as quickly as possible. The discovery rate is not a source of concern in itself. It is a measure of improved observational capability. Finding more asteroids more quickly is the intended outcome of survey improvement investments. Each new discovery represents one more object removed from the pool of unknown near-Earth asteroids, replacing unknown risk with characterized, quantified, and in almost all cases negligible probability of impact. The Minor Planet Center, operated by the International Astronomical Union and hosted at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, functions as the global repository for all observational data on asteroids and comets. Every positional measurement of a known or newly discovered small body, from professional survey programs, university observatories, or individual amateur observers, is submitted to the Minor Planet Center, which processes the data, checks it against existing orbital solutions, assigns catalog designations to new discoveries, and publishes updated orbital elements. The center's database is publicly accessible and updated in near real time. This open access model allows any researcher to query the current orbital parameters of any catalogued asteroid, enables global coordination of follow-up observation campaigns, and provides the raw astrometric data used by NASA's Center for Near-Earth Object Studies and the European Space Agency's Near-Earth Object Coordination Center to compute impact probability assessments. The Minor Planet Center is the data backbone of the global asteroid monitoring system, a facility whose contribution to planetary defense is foundational even though it operates with a modest staff and limited public profile compared to the missions and programs it supports. The main asteroid belt, despite containing millions of catalogued objects, has an average distance between adjacent objects of several 100,000 kilometers, comparable to the Earth-Moon distance. This spatial sparseness means that spacecraft transiting the belt face a very low probability of encountering any given object at close range. Every mission that has crossed the belt, beginning with Pioneer 10 in 1972, has done so without incident, navigating by pre-planned trajectories rather than real-time maneuvering to avoid obstacles. Prior to Pioneer 10's crossing, there was genuine scientific uncertainty about whether the cumulative density of small debris and dust in the belt would present a hazard to spacecraft. It did not. The Pioneer instruments detected no elevated particle flux compared to interplanetary space outside the belt, confirming that the belt's actual physical environment is far less dense than its object count alone might suggest. This sparseness has the same physical explanation as the belt's low total mass. The volume of space occupied by the belt is enormously large, and even millions of individual objects distributed through that volume result in a number density far too low to create any meaningful collision risk for a spacecraft or for another asteroid making a random transit. The first asteroid ever discovered was Ceres, identified by Italian astronomer Giuseppe Piazzi on January 1, 1801. Piazzi was cataloguing stars and noticed an object that had moved between one night's observations and the next. He tracked it for several weeks before illness interrupted his work. The positional data he had accumulated was shared with other astronomers, including Carl Friedrich Gauss, who applied a newly developed method of orbital computation to the limited dataset and predicted where the object would be found after it passed behind the Sun. The prediction was confirmed when Ceres was recovered later that year. At the time, Ceres was classified as a planet, the apparent confirmation of a predicted body in the gap between Mars and Jupiter, suggested by the Titius-Bode numerical pattern. As additional objects were discovered in the same zone, Pallas in 1802, Juno in 1804, Vesta in 1807, it became clear that the region contained a population of smaller bodies rather than a single planet, and the term asteroid was adopted to describe them. Ceres maintained an ambiguous status in popular classification for many decades. In 2006, following the International Astronomical Union's revision of planetary definitions, it was formally classified as a dwarf planet, the only one located in the inner solar system. The primary method for discovering asteroids is wide-field sky survey, systematic, repeated photography of large sky regions followed by automated comparison of successive images to identify objects that have moved against the fixed background of stars. In its earliest form, this technique required human observers to compare photographic plates by eye, blinking between images to spot any moving dot. Modern implementations are fully automated. Survey telescopes photograph the sky in tiled patterns, and processing pipelines compare each new image against reference images taken on a previous night, flagging any point of light that has shifted position. The software applies filters to eliminate false positives, satellite trails, cosmic ray hits, image artifacts, and passes genuine moving object candidates for human review or for further automated analysis. The data volumes involved are substantial. A major survey telescope can generate tens of terabytes of image data on a single clear night, containing photometric measurements of millions of individual sources. Processing this data in near real time, identifying moving objects with low false positive rates and high detection efficiency requires both sophisticated algorithms and dedicated computing infrastructure. Modern asteroid surveys are, in technical terms, large-scale data processing operations as much as they are observational astronomy programs. The Catalina Sky Survey, operated from facilities in the Catalina Mountains north of Tucson, Arizona, is one of the most productive near-Earth asteroid discovery programs currently operating. Using a network of telescopes with apertures in the range of 0.5 to 1.5 meters, the survey has been responsible for a substantial fraction of all near-Earth asteroid discoveries made over the past 2 decades. The program's high discovery rate reflects not the individual size of its telescopes, but the efficiency of its survey operations, the quality of its automated detection software, and the consistency of its nightly sky coverage. The Catalina team has refined its detection and follow-up pipeline over many years of operation and has built a network of follow-up observing capability that allows newly discovered objects, particularly those initially flagged as having uncertain orbits that might intersect Earth's, to receive additional observations promptly. Several asteroids that temporarily appeared on impact risk tables have been removed from concern through follow-up observations coordinated with or conducted by the Catalina program. It continues to operate as one of the primary discovery engines of the global near-Earth object monitoring system. The Pan-STARRS Observatory on Haleakala in Hawaii operates a 1.8-meter telescope paired with a 1.4 gigapixel camera that captures a field of view approximately 3 degrees across, roughly 6 times the apparent diameter of the full moon, in a single 15-second exposure. The camera is a mosaic of 60 detector arrays, each 64 megapixels, producing approximately 40 terabytes of image data per night of operation. This data is processed by a dedicated computing system that searches for moving objects in near real time. Pan-STARRS has been in science operation on Haleakala since 2010 and has discovered thousands of near-Earth asteroids, along with comets and other transient solar system phenomena. Its combination of wide field of view, deep sensitivity, and consistent survey cadence makes it particularly effective at detecting smaller near-Earth objects that narrower or less sensitive surveys would miss. Pan-STARRS also contributed to the discovery of the first confirmed interstellar object passing through the solar system. The elongated body designated Oumuamua, detected in 2017, illustrating the breadth of solar system phenomena that wide-field time-domain surveys can identify.
NASA's NEOWISE mission repurposed an infrared space telescope originally deployed for a full-sky survey to serve as a dedicated near-Earth object detection platform after its primary coolant supply ran out. The original WISE mission, launched in 2009, completed an all-sky infrared survey before coolant exhaustion. 2 of its detector channels remained operational afterward, and in 2013 NASA reactivated the spacecraft under the designation NEOWISE and directed it toward near-Earth object detection. The key advantage of this infrared survey approach is that it detects thermal emission from asteroid surfaces rather than reflected sunlight. All asteroids, regardless of surface albedo, absorb solar energy and re-emit it as heat, so an infrared instrument detects dark carbonaceous asteroids at comparable efficiency to bright metallic types. Ground-based optical surveys, by contrast, are substantially less sensitive to dark objects. NEOWISE therefore provided a survey less biased by albedo than ground-based surveys, detecting hundreds of near-Earth objects that optical instruments would have difficulty finding. The mission operated until its orbit decayed, and the spacecraft re-entered Earth's atmosphere in early 2024, contributing over a decade of infrared observations of the near-Earth population and providing size and albedo estimates for hundreds of asteroids whose optical survey data alone could not determine these properties. Radar astronomy, transmitting powerful radio pulses toward a nearby asteroid and analyzing the returning echo, provides physical characterization of near-Earth asteroids at a level of detail that optical observation cannot match when the target passes close enough to Earth. The timing of the echo return gives precise distance measurements. The Doppler shift of the return signal provides velocity and rotation rate information. Variations in echo intensity across different rotational phases allow construction of a 3-dimensional shape model. Surface features including craters, boulders, and topographic variations produce characteristic patterns in the delay Doppler distribution of the echo that can be resolved into detailed surface maps. Radar characterizations have transformed dozens of near-Earth asteroids from photometric data points into fully characterized physical objects with documented shapes, sizes, rotation states, and surface properties. This level of characterization is directly relevant to deflection mission design. The shape, mass distribution, and surface material properties of a target asteroid are all parameters that affect how it will respond to a kinetic impactor, and these parameters cannot be determined with sufficient precision from optical observation alone when precision matters for mission design. The Goldstone Solar System radar in California and the Arecibo Observatory in Puerto Rico were the 2 primary facilities used for near-Earth asteroid radar characterization. Arecibo, with its 305-meter dish built into a natural limestone depression in Puerto Rico's karst landscape, was the most powerful radio telescope in the world for several decades and produced radar images of near-Earth asteroids at resolutions unmatched by any other facility. The collapse of Arecibo's receiver platform in December 2020, following the failure of support cables, ended a program of planetary radar observations that had characterized hundreds of objects over several decades. Goldstone, a 70-meter steerable dish operated by NASA's Jet Propulsion Laboratory in the Mojave Desert, continues as the primary operational planetary radar facility. Its sensitivity is lower than Arecibo's was, requiring that objects pass somewhat closer to Earth to achieve comparable imaging resolution. The planetary defense community has been evaluating options for restoring or supplementing radar characterization capability, since no other observing technique produces comparable physical information for objects making close Earth approaches at the distances where radar is effective. A newly discovered asteroid's initial orbital solution carries substantial uncertainty because it is derived from a short observational arc, the limited span of sky the object has been seen to traverse. The range of orbits consistent with only a few nights of observations is wide enough to include trajectories spanning from entirely benign to, in some cases, Earth intersecting. As additional observations are obtained over subsequent nights and weeks, each new positional measurement constrains the set of possible orbits further, narrowing the range until a well-determined solution is reached. For most newly discovered objects, this refinement quickly establishes a non-threatening trajectory. For objects whose initial orbital uncertainty spans a range that includes possible Earth approaches, the standard response is intensive follow-up observation to resolve the uncertainty as rapidly as possible. The duration of elevated concern for any given object depends on how quickly follow-up observations can be obtained and how rapidly the additional data narrows the orbital uncertainty. In most cases, a few weeks of additional observation is sufficient to resolve the situation. In nearly all cases to date, the resolved orbit has confirmed the object to be non-threatening. The Torino scale is a 10-point risk communication system used to convey the impact hazard of a newly discovered near-Earth object to the public. Adopted by the International Astronomical Union in 1999 and named for Turin, Italy, where it was formally presented, the scale assigns integer values based on the combination of an object's computed impact probability and the energy it would release if it were to strike Earth. A rating of 0 indicates no hazard. The object poses no meaningful impact risk. Ratings from 1 through 3 describe objects with low but non-zero impact probabilities that merit continued scientific monitoring but warrant no public concern. Higher ratings represent increasing combinations of probability and consequence. A rating of 10 is reserved for a confirmed collision capable of global catastrophe. No asteroid has ever been rated above 4. That maximum was reached briefly by asteroid Apophis in late 2004, following initial orbital calculations suggesting a non-trivial 2029 impact probability. Additional observations obtained over the following months reduced the rating to 0. The Torino scale is a communication tool rather than a scientific instrument. The underlying calculations use continuous probability and energy metrics, and the Torino rating is assigned as a summary of those calculations for public reporting purposes. The Palermo technical scale is a continuous logarithmic measure used by scientists and planetary defense analysts to assess the relative hazard of a newly discovered near-Earth object compared to the statistical background rate of random impacts. Unlike the Torino scale, which uses discrete integer values for public communication, the Palermo scale provides a precise numerical comparison between the calculated impact probability of a specific object, weighted by the energy it would release, and the probability of a random impact of comparable or greater energy occurring during the same time window. A Palermo scale value of -2 means the specific object is 100 times less hazardous than the background statistical rate for its size and encounter window. A value of 0 means it is exactly equal to the background rate. A value above 0 is rare and scientifically significant, indicating that the specific object represents a greater hazard than the statistical background would predict. In practice, most newly discovered objects appear on risk tables with strongly negative Palermo scale values that become more negative as additional observations reduce orbital uncertainty. The scale provides a consistent basis for prioritizing follow-up observing resources across the catalogue of objects under assessment at any given time. NASA's Center for Near-Earth Object Studies, CNEOS, located at the Jet Propulsion Laboratory in Pasadena, California, continuously computes and maintains publicly accessible databases of close approach predictions and impact risk assessments for all known near-Earth asteroids. The center ingests observational data from the Minor Planet Center, computes orbital solutions using JPL's own dynamical models, propagates those solutions forward to identify predicted close approaches, and calculates associated impact probabilities. Both the close approach tables and the impact risk tables are published on the CNEOS website in near real time and updated as new observations become available. This public availability is a deliberate policy choice. The US government's position has been that open, timely information about close asteroid approaches and impact risk assessments is preferable to selective disclosure, and that public confidence in the monitoring system is best maintained by transparency. The same information used by NASA planetary defense analysts is accessible to researchers, journalists, and any member of the public who chooses to consult it. CNEOS also produces the detailed orbital solutions used as inputs for deflection mission planning and for the international coordination processes carried out through IAWN and SMPAG. On February 15, 2013, an asteroid estimated at approximately 20 meters in diameter entered Earth's atmosphere over the Chelyabinsk region of Russia, disintegrating in an airburst at an altitude of roughly 23 kilometers. The event released energy equivalent to approximately 30 times the yield of the Hiroshima atomic bomb. The resulting shockwave shattered windows across approximately 3,000 square kilometers, injuring roughly 1,500 people, the large majority from cuts caused by broken glass. Several communities reported structural damage, including partial roof collapse at a factory in Chelyabinsk. No direct fatalities were attributed to the impactor. The event was captured by dashboard cameras and security systems across the region, producing an unusually complete observational record. Scientific analysis of the footage and of the infrasound and seismic signals generated by the airburst allowed researchers to estimate the object's size, mass, composition, and approach trajectory with greater precision than is typically possible for undocumented atmospheric impacts. The Chelyabinsk event is the most significant asteroid impact affecting a populated area in recorded history. It prompted substantial discussion among the planetary defense community and within governmental bodies about the adequacy of existing survey programs for detecting objects in the tens of meters size range that had not been a previous survey priority. The Chelyabinsk asteroid was not detected before its arrival. It approached from the direction of the Sun, placing it in the region of sky that ground-based survey telescopes cannot observe due to solar glare. This solar blind spot is a persistent, structural limitation of ground-based planetary defense surveillance. Telescopes on Earth's surface must avoid pointing in the direction of the Sun during observations, which means that asteroids on approach trajectories from the general sunward direction are invisible to ground-based surveys until they emerge from the solar glare, often at distances and on timelines that provide hours of warning rather than years. The Aten and Atira orbital families are particularly susceptible to this limitation, as their orbits keep them near the Sun in Earth's sky for extended periods. The Chelyabinsk object's approach trajectory placed it in this blind zone throughout the final portion of its approach. Space-based observatories observing from positions that allow them to look toward the inner solar system without solar interference can address this gap. The NEO Surveyor mission, designed to operate near the Sun-Earth L1 Lagrange point, is specifically positioned to detect asteroids approaching from directions that ground-based surveys cannot cover, including the class of sunward approaching objects represented by the Chelyabinsk impactor. Asteroid Apophis, initially designated 2004 MN4, received a Torino scale rating of 4 in late 2004, the highest ever assigned to a real asteroid, following orbital calculations indicating a non-trivial probability of Earth impact in April 2029. The rating prompted immediate intensive follow-up observation from multiple observatories. Initial probability estimates for the 2029 impact briefly reached approximately 2.7% before declining as more observations constrained the orbit. The 2029 impact was ultimately ruled out by early 2005. Subsequent analysis identified a separate concern. The 2029 close approach would carry Apophis through a small region of space called a gravitational keyhole, and traversal of the keyhole would place the asteroid on an impact trajectory for a return encounter in 2036. Further observations ruled out that possibility as well. Apophis's orbit has since been calculated with sufficient precision to confirm no impact risk through at least 2068. The Apophis case is frequently cited in planetary defense literature as an example of the detection and assessment system functioning as designed. Initial identification of a potentially hazardous object, rapid mobilization of follow-up resources, progressive orbital refinement, and final resolution of the uncertainty in the non-threatening direction, all within weeks to months of the initial discovery. Asteroid Apophis, approximately 370 meters in diameter, will pass approximately 25,700 kilometers above Earth's surface on April 13, 2029. That distance places it within the orbital band occupied by geostationary communications and weather satellites, which operate at approximately 35,786 kilometers above the equator. At that distance, Apophis will be visible without optical aids from parts of Europe, Africa, and Western Asia, appearing as a moving point of light over the course of several hours. The 2029 flyby will be the closest confirmed approach of an asteroid of this size to Earth in recorded observational history. It will be observed intensively by ground-based optical telescopes and radar facilities, and potentially by dedicated spacecraft. The encounter will also allow Earth's gravity to measurably alter Apophis's orbital parameters, an event of scientific interest in its own right, as it will provide direct observational data on how a planetary gravitational field perturbs an asteroid during a close approach. Multiple spacecraft mission proposals have been put forward for rendezvous with Apophis before or during the 2029 flyby, motivated by both scientific interest in characterizing the asteroid at close range and by the planetary defense value of precision measurements made during the encounter. The 2029 close approach of Apophis will allow Earth's gravity to measurably alter the asteroid's orbital period, eccentricity, and orbital plane orientation. The exact magnitude of these changes depends on the precise approach geometry, specifically how closely Apophis passes relative to Earth's center of mass and at what angle it approaches. Computing the post-encounter orbit with precision requires knowing the pre-encounter orbit to a corresponding level of accuracy, which motivates the intensive observational campaigns planned for the period between now and April 2029. The 2029 encounter will also subject Apophis to tidal forces, differential gravitational acceleration across the width of the asteroid, that may affect its surface structure and rotation state. These effects are most significant for objects with loosely consolidated interiors, and if Apophis has a rubble pile structure, the close approach may trigger surface movement or changes in rotation rate that would be detectable by sufficiently sensitive instruments. The 2029 flyby therefore provides an opportunity to study, in real time and at close range, the gravitational and tidal effects of a planetary encounter on an asteroid. Processes that shape the properties of near-Earth asteroids over long timescales, but cannot otherwise be observed directly. In January 2023, near-Earth asteroid 2023 BU passed approximately 3,600 kilometers above Earth's surface, inside the orbital altitude of geostationary satellites and among the closest approaches on record for any catalogued asteroid. The object was estimated at approximately 4 meters in diameter, well below the size threshold at which a ground impact would cause any meaningful damage. 2023 BU was discovered 4 days before its closest approach by amateur astronomer Gennady Borisov and was quickly followed up by observatories worldwide, which confirmed the trajectory and confirmed that the object posed no risk. The event illustrated the current capabilities and limitations of the planetary defense system simultaneously. An object of 4 meters can be found a few days before a very close flyby confirmed to be non-threatening and tracked through its encounter. An object of 50 or 100 meters on a similar trajectory would represent a substantially different situation. Its discovery just days before closest approach would leave insufficient time for deflection, and its impact, had it been on a collision course, could have caused significant damage. The different implications of these two scenarios underscore why size matters in evaluating close approach reports and why survey completion at the smaller size ranges remains a priority. When a rubble pile asteroid passes close enough to a planet, tidal forces, differential gravitational acceleration across the body's width, can affect its internal structure and surface. The gravitational pull of the planet is slightly stronger on the near side of the asteroid than the far side, creating a net stretching effect. For a loosely bound aggregate, this stress can shift the positions of internal fragments, trigger surface mass movements, or in cases of extreme proximity, strip surface material that then enters orbit around the asteroid. Tidal interactions during planetary flybys have been proposed as a formation mechanism for the ring systems observed around some outer solar system small bodies, and as a contributor to the equatorial ridges seen on some near-Earth asteroids. Materials centrifugally shed during a rotationally accelerated phase triggered by tidal interaction. These processes operate passively on timescales ranging from single close approach events to repeated encounters over millions of years. Understanding tidal effects on rubble pile asteroids is relevant to planetary defense because any asteroid that has experienced close planetary encounters will have had its physical properties affected by those encounters, and those modified properties will in turn affect how the asteroid responds to a deliberate deflection attempt. Statistical analysis of the impact cratering record and the observed frequency of fireball events in Earth's atmosphere indicates that impacts by asteroids large enough to cause significant regional destruction occur at an average rate of roughly once every few thousand years. This is a long-run statistical rate, not a prediction of any specific event. The most recent event at approximately this energy scale was the 1908 Tunguska airburst, which occurred in a remote, sparsely populated region of Siberia. The absence of events of comparable magnitude since then is consistent with the statistical rate but does not preclude a recurrence at any time. The rate estimate carries significant uncertainty. The observational record from which it is derived covers a limited time span, and the calculation requires assumptions about the size-frequency distribution of near-Earth asteroids that are themselves based on incomplete survey data. Improving the estimate is among the secondary benefits of comprehensive near-Earth asteroid surveys, which provide direct population data that feeds into impact frequency calculations. The current best estimates indicate that impacts capable of destroying a large city or generating significant regional tsunamis occur infrequently enough that they are unlikely in any given human lifetime, but frequently enough on longer timescales to be treated as a serious actuarial risk. In asteroid tracking terminology, close approach is a relative term that describes any predicted passage of a near-Earth asteroid within a defined distance of Earth, without implying any level of physical danger. An asteroid passing at 10 lunar distances, approximately 3.8 million kilometers, is described as a close approach in the context of solar system dynamics, but poses no threat of any kind and would be invisible from Earth's surface without instruments. The use of the phrase close approach in public reporting about asteroids has repeatedly generated confusion and concern disproportionate to the actual assessed risk, because the term conveys proximity relative to the scale of the solar system rather than proximity in any sense meaningful to people on Earth's surface. The only metric directly relevant to impact risk is whether an asteroid's orbit intersects or comes into sufficient proximity to Earth's orbit in a geometry that allows an actual encounter, and whether the computed probability of that encounter is above a meaningful threshold. Close approach reports from planetary defense databases include encounters at tens of millions of kilometers that are of scientific documentation interest but carry no hazard whatsoever. Reading these reports requires understanding the distance scale involved, not just the designation. Earth receives approximately 100 tons of interplanetary material per day, primarily in the form of microscopic dust particles and small meteoroids that ablate completely in the upper atmosphere. This continuous influx represents the low end of the size distribution of solar system material that intersects Earth's orbital path. The individual events span a wide range. Microscopic grains produce no visible phenomenon. Centimeter-scale particles generate brief meteors. Larger objects produce fireballs that may be visible in daylight and produce audible sonic booms across wide areas. Objects large enough to survive atmospheric transit and reach the ground as meteorites are rare by comparison, with a small number of recovered falls documented globally per year. The infrasound network operated by the Comprehensive Nuclear Test Ban Treaty Organization provides a continuous statistical record of larger fireball events, those releasing a kiloton or more of energy in the atmosphere. And this data has been used to construct an observational frequency distribution of atmospheric impacts across the size range from 1 meter up to Chelyabinsk scale. This observational record provides an independent verification of population estimates derived from telescopic surveys and serves as a continuously updated empirical baseline for impact frequency statistics. The Tunguska event of June 30, 1908 is the largest documented asteroid impact in recorded history. An object estimated at 50 to 80 meters in diameter entered Earth's atmosphere over the remote Podkamennaya Tunguska River basin in central Siberia and disintegrated in an airburst before reaching the ground. The released energy, estimated at 10 to 15 megatons of TNT equivalent, flattened approximately 2,000 square kilometers of forest. The blast wave was recorded by barograph stations around the world and circled the globe twice. Eyewitnesses at distances of tens of kilometers described intense heat, a column of fire, and a shock wave that knocked people and livestock off their feet. No confirmed fatalities resulted, attributable primarily to the extreme sparseness of population in the impact region. The site was not reached by a scientific expedition until 1927, when Leonid Kulik's team documented the characteristic radial pattern of felled trees pointing outward from the explosion center, with a small zone of standing but stripped trees directly beneath the burst point, confirming the airburst interpretation. The absence of a crater and the absence of recovered meteoritic material are both consistent with the complete atmospheric disintegration of the impactor before reaching the surface. No crater formed at Tunguska because the impacting object disintegrated in an airburst at approximately 8 to 10 kilometers altitude before reaching the ground. An airburst distributes impact energy across a broad area rather than concentrating it at a single point, producing a different and in some respects more destructive damage pattern than a ground impact of comparable energy. The Tunguska burst released approximately 10 to 15 megatons of energy, roughly 1,000 times the yield of the Hiroshima bomb, in a downward and outward directed blast that propagated through the forest below as an overpressure wave. Trees within the damage zone were stripped of bark, scorched, and flattened, with the direction of fall-off providing a map of the blast geometry. The barograph records from stations across Europe and Asia, collected in the hours following the event, confirmed the energy release independently and established the timing and approximate location of the detonation before any ground survey had been conducted. The Tunguska case illustrates that atmospheric disintegration does not render an impactor harmless. A 50 to 80 meter body that never touched the ground caused damage equivalent to a large nuclear weapon over an area twice the size of Greater London. The atmosphere absorbed the energy, but did not eliminate the consequences. The Chicxulub impact, approximately 66 million years ago, involved an asteroid or comet estimated at 10 to 15 kilometers in diameter that struck the Yucatan Peninsula of what is now Mexico. It is the best documented and most scientifically analyzed large impact event in Earth's geological record and is widely accepted as a major cause of the mass extinction at the end of the Cretaceous period. The event that eliminated approximately 75% of all species on Earth, including all non-avian dinosaurs. The evidence base for this conclusion includes a 180-kilometer-wide subsurface impact structure identified under the northern Yucatan Peninsula and adjacent Gulf of Mexico, a globally distributed layer of iridium, an element rare in Earth's crust but relatively abundant in some asteroid types, at precisely the Cretaceous-Paleogene geological boundary, shocked quartz and glass spherules distributed globally in the same boundary layer, and soot layers consistent with large-scale post-impact wildfires. The hypothesis connecting the boundary iridium anomaly to an extraterrestrial impact was first proposed in 1980 by Luis and Walter Alvarez and has since been confirmed through independent analyses of boundary layer samples from hundreds of sites on multiple continents and in ocean sediment cores. The Chicxulub impact released energy estimated at approximately 100 teratons of TNT equivalent, roughly 2 billion times the yield of the largest nuclear weapon ever detonated. The immediate effects included a fireball and thermal pulse that ignited large-scale wildfires across much of North America, mega tsunamis generated by the impact into a shallow sea that propagated across ocean basins, and an ejecta cloud of vaporized and melted rock distributed globally that re-entered the atmosphere and heated the upper air enough to ignite surface fires in regions not directly exposed to the initial fireball. The longer-term effects were driven by stratospheric loading of soot, sulfurous aerosols, and fine dust that blocked incoming solar radiation for months to years, suppressing photosynthesis globally and causing a prolonged period of reduced surface temperatures, the impact winter. The The collapse of photosynthesis at the base of food chains, sustained over a period long enough to eliminate the reproductive capacity of most large land animals, was the primary mechanism by which the mass extinction was propagated globally. The organisms that survived, small, metabolically flexible, capable of exploiting a broad range of food sources, included the lineages that would give rise to the dominant fauna of the subsequent Cenozoic era. Earth's geological record contains more than 190 confirmed impact craters, a number that substantially underrepresents the actual frequency of significant impacts over the planet's history. Multiple ongoing geological processes continuously erase the cratering record. Erosion by wind and water degrades crater rims and fills basins. Plate tectonics subducts oceanic crust, destroying any impact structures that formed on ocean floor material, which covers more than 70% of Earth's surface. And volcanic activity buries older terrains under new rock sequences. The 190 confirmed structures are therefore a biased sample, concentrated in geologically stable continental shields and in younger terrains not yet fully eroded. They represent a small fraction of the actual impact history. The Moon's surface, which lacks the active geological processes that erase Earth's cratering record, provides a more complete record of the impact flux in the inner solar system. Lunar crater density studies, calibrated against radiometric ages of Apollo samples, indicate that the impact rate in the early solar system was substantially higher than it is today and has declined over time to the current lower but non-zero rate. Barringer Meteor Crater in northern Arizona, also known as Meteor Crater, is approximately 1.2 kilometers in diameter and 170 meters deep. It was formed approximately 50,000 years ago by an iron meteorite estimated at roughly 50 meters in diameter, traveling at approximately 12 kilometers per second. The impactor delivered energy equivalent to approximately 10 megatons of TNT, excavating the crater in seconds. The site's location in the arid Sonoran Desert has minimized erosion, preserving it in near original condition, the best preserved large impact crater on Earth and among the most thoroughly studied. Barringer Crater was the first terrestrial structure confirmed as an impact crater through geological evidence, rather than simply identified as a circular topographic feature. This confirmation, achieved by Eugene Shoemaker in the 1950s through the identification of coesite and stishovite, high-pressure silica polymorphs that can only form under the shock conditions of hypervelocity impact, established the diagnostic criteria subsequently used to confirm crater origins worldwide. The crater demonstrated that impacts capable of leaving large, geologically persistent structures had occurred within the span of modern human prehistory and were not confined to the ancient geological past. The Vredefort structure in South Africa, with a diameter of approximately 300 kilometers, is the largest confirmed impact structure on Earth. It was formed approximately 2 billion years ago by an impactor estimated at 10 to 15 kilometers across, comparable in size to the Chicxulub impactor. The original crater has been extensively modified over 2 billion years. The rim has been eroded away, and what remains is a deeply exhumed structure, a central dome of ancient rock uplifted during post-impact crater floor rebound, surrounded by a ring of hills representing the eroded inner portion of the original crater structure. The impact origin of the Vredefort structure was confirmed through the identification of shocked quartz, planar deformation features in mineral grains, and pseudo-tachylite, a glass-like material formed by frictional melting during the impact event, at multiple locations within the structure. These shock metamorphism indicators are diagnostic of hypervelocity impact and cannot be produced by any known endogenous geological process. Vredefort, together with the Sudbury structure in Canada and the Chicxulub structure, represents the three largest confirmed impact structures on Earth, all formed by impactors of broadly comparable size distributed across approximately 2 billion years of geological history. Some researchers have proposed that mass extinction events beyond the end Cretaceous may have had impact contributions, though the evidence is less definitive than for the Chicxulub case. The end Permian extinction approximately 252 million years ago, which eliminated an estimated 96% of marine species and 70% of terrestrial vertebrate species, is currently attributed primarily to the Siberian Traps volcanic eruptions, a massive outpouring of basaltic lava that released large quantities of greenhouse gases and caused severe environmental disruption. Some researchers have proposed an impact component, but no impact structure of appropriate age and size has been confirmed. The end Triassic extinction approximately 201 million years ago is associated with another large igneous province, and the Manicouagan impact structure in Quebec, which dates from approximately the same period, has been proposed as a contributor, though the relationship between the impact and the extinction remains uncertain. The field of impact extinction linkage research is complicated by the difficulty of precise age correlation across different geological archives and by the challenge of distinguishing impact effects from coincident large-scale volcanic effects. The Chicxulub case remains the only large-body impact for which both the physical evidence of the impact and the biological consequences are well constrained in the geological record. The Moon's surface preserves a record of the bombardment history of the inner solar system in a form that Earth's active geology has largely obliterated. Analysis of lunar samples from Apollo missions combined with crater size frequency distribution studies indicates that the Moon experienced a period of elevated impact flux approximately 4.1 to 3.8 billion years ago, a period referred to as the late heavy bombardment. The cause of this elevated flux is debated. One widely discussed hypothesis proposes that gravitational instabilities in the outer solar system during this period caused a large population of objects from the outer solar system to be scattered inward, temporarily increasing the impact rate on the terrestrial planets. Earth would have experienced the same elevated flux as the Moon during this period, with impacts far more frequent and energetic than those occurring in the present era. Some researchers have proposed that this period of intense bombardment may have delivered significant quantities of water and organic material to Earth, contributing to the chemical inventory that the subsequent emergence of life required. Others have argued that the bombardment would have been severe enough to repeatedly sterilize any surface environment where life might have been developing, making the window between the end of the late heavy bombardment and the first evidence of life in the geological record scientifically significant. Some researchers have proposed that asteroid and comet impacts during Earth's early history may have delivered a significant fraction of the planet's water inventory and organic molecule supply, potentially contributing to the chemical conditions necessary for life's emergence. This exogenous delivery hypothesis is supported by several lines of evidence. Carbonaceous chondrite meteorites, ancient primitive stones derived from C-type asteroids, contain amino acids, nucleobases, sugars, and other organic compounds, as well as water chemically bound in clay minerals. The hydrogen isotopic composition of Earth's water resembles that of certain asteroid types more closely than that of the solar nebula gas, suggesting that a portion of Earth's water was delivered by impacting bodies after the planet formed. Laboratory analysis of samples returned from carbonaceous asteroids by the Hayabusa 2 and OSIRIS-REx missions has confirmed the presence of amino acids and organic compounds in concentrations and diversities broadly consistent with the meteorite record. The exogenous delivery hypothesis does not require that life itself arrived from space, only that some fraction of the molecular raw materials and water that supported life's eventual emergence may have been delivered by asteroid and comet impacts during the early period of heavy bombardment. An asteroid in the 25 to 50 meter size range striking land would release energy broadly comparable to a nuclear weapon in the single to tens of megatons yield range, causing destruction over an area of hundreds of square kilometers. The specific consequences depend on the object's composition, density, approach velocity, and entry angle, as well as whether it arrives as a cohesive body or fragments during atmospheric transit. A solid iron meteorite in this size range is more likely to penetrate to low altitude or reach the ground before releasing its energy, while a stony or carbonaceous body is more likely to disintegrate at altitude in an airburst. Ground impact produces a crater and concentrated local destruction. Airburst distributes energy over a wider area with a lower peak intensity per unit area. Either outcome over a densely populated urban area would cause casualties and structural damage on a scale comparable to the largest natural disasters in modern recorded history. Objects in this size range are too small to cause effects detectable beyond the local region. They would not disrupt global climate or threaten food supply systems, but their potential to eliminate a major population center if they arrived undetected is the primary motivation for extending survey capability below the 140-meter threshold. An asteroid 140 meters or larger striking Earth would release energy equivalent to hundreds of megatons of TNT, producing regional destruction extending well beyond the immediate impact zone. At this size, the consequences include ground overpressure and wind velocities capable of destroying reinforced structures across a radius of tens of kilometers, thermal radiation capable of igniting fires at greater distances, and in coastal or shallow water impacts, tsunami generation affecting coastlines across a wide region. An ocean impact by a 140-meter asteroid would not produce the global climate effects associated with larger impactors, but the tsunami hazard could affect multiple countries and cause casualties in the millions if sufficient warning time for evacuation were not available. The 140-meter threshold corresponds directly to the size limit of NASA's current survey mandate under the George E. Brown Act, which directs the agency to catalogue 90% of near-Earth objects larger than this diameter. This mandate reflects a policy judgment that objects of this size and above represent a risk level requiring systematic national and international effort to address, while objects below this size, though potentially locally catastrophic, represent a different tier of risk management for which survey completion is not yet feasible with current technology. A 1-kilometer asteroid impact would release energy in the range of tens of thousands of megatons, sufficient to inject large quantities of dust, aerosols, and combustion products into the stratosphere and trigger a period of global climate disruption. The duration and severity of this disruption would depend on the impactor's composition, the location of the impact, and the atmospheric conditions at the time, but the general mechanism is well understood from the Chicxulub precedent at larger scale. Stratospheric particulate loading reduces incoming solar radiation, suppressing photosynthesis and causing surface temperatures to decline. Global agricultural productivity would be affected, with the most severe impacts in regions already near food production margins. The economic, political, and social disruptions from a prolonged period of reduced agricultural output could compound the direct physical effects. Human civilization and most complex life would be expected to survive a 1-kilometer impact. The effects, while severe, are several orders of magnitude below those of Chicxulub, but the event would represent a civilizational stress test with no precedent in recorded history. The residual uncertainty in the survey of kilometer-scale near-Earth objects, the few percent estimated to remain undiscovered, is the primary actuarial basis for the concern about this size class. Asteroids larger than approximately 5 to 10 kilometers are considered capable of causing mass extinction events if they were to strike Earth, impacts comparable in consequence to the Chicxulub event. For this size class, the completeness of the current near-Earth asteroid survey is highest. Scientists estimate that more than 95% of near-Earth asteroids larger than 1 kilometer have been discovered, none of them currently on a collision course with Earth. The remaining uncertainty at the largest scales arises not from incompleteness in the near-Earth asteroid survey but from the separate population of long-period comets, objects on highly elliptical orbits originating in the outer solar system that make periodic or one-time passages through the inner solar system. These objects are inherently difficult to detect far in advance because they spend most of their orbital period in the outer solar system beyond the range of current survey instruments, and they may arrive on impact trajectories with limited warning time. Long-period comets represent a distinct and partially unaddressed category of impact risk, and addressing this gap requires either survey assets capable of detecting these objects in the outer solar system during their long approach, or deflection capabilities that can operate on shorter warning timelines than are currently practical. An asteroid impacting an ocean would generate tsunamis whose size depends on the energy of the impact and the geometry of the impact site. Shallow coastal or continental shelf impacts produce tsunami waves more efficiently than deep ocean impacts. However, even deep ocean impacts at sufficient energy levels generate waves that can propagate across ocean basins and shoal destructively at coastlines. Estimates of tsunami generation by asteroid impacts indicate that a 200-meter impactor striking deep ocean could produce open ocean waves several meters high that amplify as they approach coastal shallows, potentially reaching tens of meters in height at affected coastlines. A 500-meter impactor in similar conditions would produce substantially larger effects. The affected coastlines could be anywhere in the ocean basin, at distances of thousands of kilometers from the impact site. Because the ocean covers more than 70% of Earth's surface, a randomly placed asteroid impact is more likely to occur in ocean than on land, making oceanic impact scenarios of particular humanitarian relevance. The current distribution of global population, with large fractions living in low-elevation coastal zones, means that oceanic impact tsunami hazard is geographically concentrated in precisely the areas of highest population density. Asteroids enter Earth's atmosphere at velocities typically between 12 and 20 kilometers per second, varying with the orbital geometry of the encounter. At these velocities, the air in front of the descending object cannot flow around it and is compressed and heated to temperatures of tens of thousands of degrees, forming a luminous sheath of ionized gas around the leading face. This aerodynamic heating ablates material from the impactor's surface, which vaporizes and contributes to the luminous trail visible as a fireball. As the object descends into progressively denser atmospheric layers, aerodynamic forces increase. For objects composed of relatively weak material, loosely consolidated stone or carbonaceous matter, these forces can exceed the tensile strength of the body at altitude, causing explosive fragmentation in an airburst. For denser, stronger objects, particularly iron-nickel meteorites, the body may retain cohesion to lower altitudes before depositing energy at the surface or forming a crater. The transition between airburst and ground impact depends on the object's composition, internal structure, and approach trajectory, and cannot be determined with confidence from orbital and spectral data alone. This introduces uncertainty into impact consequence modeling that can only be reduced by close proximity physical characterization of a specific threatening object prior to a deflection mission. The probability of a civilization-threatening asteroid impact in any given century is estimated at less than 1 in 1 million. This is a very low probability in the actuarial sense, but not zero, and it operates against a background of extremely high potential consequences. The standard framework for evaluating whether to invest in low probability, high consequence risk mitigation, used across domains including nuclear safety, pandemic preparedness, and financial system resilience, treats the expected cost of an event as the product of its probability and the magnitude of potential harm aggregated across the affected population. By this metric, the expected cost of a civilization-scale asteroid impact, even at very low probability, is non-trivial. Unlike most natural hazards, asteroid impacts are in principle preventable given sufficient warning time and appropriate technology. The cost of maintaining the survey and deflection infrastructure required to prevent the worst outcomes is small relative to the consequences being prevented. The DART mission demonstrated that the primary deflection technology works. These factors taken together constitute the policy basis for sustained governmental investment in planetary defense programs across the United States, Europe, and increasingly other spacefaring nations. Impact energy, expressed in megatons of TNT equivalent, is the standard metric used to characterize the destructive potential of a given asteroid impact and to communicate that potential to policymakers and the public. 1 megaton of TNT equivalent corresponds to the energy released by 1 million metric tons of conventional explosive, a unit standardized during the nuclear weapons era for describing thermonuclear device yields. Expressing asteroid impact energies in the same units as nuclear weapons yields allows direct comparison and provides a reference scale that policymakers without specialized planetary science training can interpret. The Chelyabinsk event released approximately 0.5 megatons. The Tunguska event released 10 to 15 megatons. A 140-meter impact delivers several hundred megatons. A 1-kilometer impact reaches the range of tens of thousands of megatons. The Chicxulub event is estimated in the range of 100 billion megatons. The progression across these size scales illustrates the steep energy scaling of impact consequences with size and explains why the 140-meter threshold is treated as the practical lower boundary of the size range that warrants organized global response rather than local or regional emergency management. An undetected asteroid striking a major ocean basin without warning could produce coastal flooding affecting tens of millions of people within hours, underscoring why early detection is a humanitarian concern rather than solely a scientific one. The distinction between early and late detection is the distinction between an event that can potentially be prevented and one for which only post-impact response is available. With decades of warning, a moderate-sized kinetic impactor mission can deflect most near-Earth asteroids in the hazardous size range. With a year of warning, options narrow significantly. With weeks or days, deflection is not operationally feasible for any current or near-term technology, and the response reduces to emergency management.
evacuation of predicted impact zones, tsunami warning system activation, and post-impact humanitarian assistance. The populations living in tsunami inundation zones in major ocean basin coastlines are among the most numerous and the least easy to evacuate quickly. Every improvement in survey sensitivity and cadence that finds threatening asteroids earlier converts potential emergency response scenarios into potential deflection scenarios, which is why survey investment is characterized in policy discussions as the highest leverage component of the planetary defense system. Researchers studying the societal dimensions of planetary defense have identified the communication and governance challenges associated with a confirmed long-range impact prediction as a distinct area of concern, separate from the technical problem of deflection. A confirmed asteroid impact prediction with decades of warning would require governments to communicate probabilistic information about a future catastrophe to a global public over an extended period, a communication challenge without precedent. Studies and exercises have examined how governmental and international structures would manage the escalation from initial detection to public disclosure, mission planning, and, if necessary, the coordination of a deflection campaign involving multiple national space agencies. These exercises have identified coordination bottlenecks and decision authority gaps that ongoing protocol development is working to address. The economic and social effects of a publicly known long-range impact prediction affecting investment, insurance, migration, and political stability over years or decades are also studied as a secondary risk that could compound the direct physical consequences of the eventual impact. Planetary defense planning therefore encompasses not only the technical problem of finding and deflecting threatening asteroids, but the governance and communication infrastructure required to manage the societal response to a confirmed threat. NASA's Planetary Defense Coordination Office, established in 2016, is the agency's designated body for coordinating detection, tracking, characterization, and mitigation activities related to potentially hazardous asteroids and comets. Before its creation, NASA's planetary defense work was distributed across multiple program offices without unified oversight. The PDCO consolidated these activities under a single organizational structure, established formal interagency coordination mechanisms with FEMA, the Department of Defense, and the State Department, and created a designated institutional point of contact for communication with international partners and the public. The office oversees NASA's asteroid survey programs, manages the NEO Surveyor mission development, and participates in international coordination bodies, including the International Asteroid Warning Network and the Space Mission Planning Advisory Group. It also handles external communication about close asteroid approaches and impact risk assessments, maintaining publicly accessible information channels and issuing statements when newly discovered objects receive public attention. The establishment of the PDCO reflected a formal institutional commitment by NASA and the US government to treat planetary defense as an organized, funded, ongoing program rather than an ad hoc scientific research area. The SpaceGuard survey goal, established by a 1992 congressional directive to NASA, called for the discovery and cataloging of 90% of all near-Earth asteroids larger than 1 kilometer within 10 years. The directive followed a scientific workshop organized at NASA's request that had quantified the near-Earth asteroid impact risk and recommended a systematic survey to characterize the kilometer scale and larger population. The goal motivated the establishment and expansion of several ground-based survey programs, including Spacewatch, Linear, and NEAT. These programs, working over the following decade and a half, built the catalog of known near-Earth asteroids from hundreds to thousands of objects. The 1 kilometer completion threshold was substantially achieved by approximately 2010. The key outcome of the SpaceGuard effort was confirming that the most dangerous class of near-Earth asteroids, those capable of causing global climate disruption, had been substantially inventoried, and that none of the known population was on an impact trajectory. This replaced what had been an almost entirely unknown risk with a characterized, quantified, and currently non-threatening assessed population. The SpaceGuard survey represented the first systematic attempt in human history to inventory a category of natural hazard affecting the entire planet. The NASA Authorization Act of 2005, carrying the name of the late Congressman George E. Brown Jr., extended NASA's survey mandate to include 90% of all near-Earth objects larger than 140 meters in diameter. This expanded goal required substantially more capable survey instruments than those sufficient for the kilometer-scale survey.
The 140-meter population is estimated to be roughly 10 times larger in number than the kilometer-scale population, and the individual objects are correspondingly fainter and require either larger telescopes, more sensitive detectors, or both to detect at survey-relevant distances. As of the mid-2020s, current ground-based surveys have found approximately 40% of the estimated 140-meter and larger near-Earth asteroid population, well short of the 90% target. The NEO Surveyor space-based mission, recommended by the 2020 Planetary Science and Astrobiology Decadal Survey and approved for development, is expected to substantially accelerate progress toward this goal by detecting asteroids in infrared wavelengths from space, accessing the sunward approach directions that ground-based surveys cannot cover, and detecting dark asteroids that optical surveys undercount. Without NEO Surveyor or a comparable space-based capability, current projections indicate that completing the 140-meter survey mandate would take several additional decades at current ground-based survey rates. The European Space Agency operates the Near-Earth Object Coordination Centre, NEOCC, which maintains an independent asteroid tracking catalogue and collaborates with NASA's Centre for Near-Earth Object Studies in monitoring the near-Earth population and assessing impact risks. Based at ESA's Space Astronomy Center near Madrid, Spain, the NEOCC computes orbital solutions for known near-Earth objects using software developed independently from NASA's systems. This redundancy is a deliberate feature. When two organizations using different computational pipelines and different software implementations arrive at consistent impact probability assessments, the agreement validates both results. When the assessments diverge for a newly discovered object, which can occur when observational data is sparse and orbital uncertainty is large, the discrepancy indicates that additional observations are needed before either assessment can be considered reliable. The NEOCC also operates and coordinates a network of follow-up telescopes capable of rapidly obtaining additional observations of newly discovered potentially hazardous objects. ESA and NASA share data through standardized interfaces and compare risk assessments regularly through established coordination mechanisms. Both agencies publish their impact probability tables publicly, providing the global research community and the public with access to independent, cross-validated impact risk information. The International Asteroid Warning Network, IAWN, is a global consortium of observatories, space agencies and research institutions coordinated by the United Nations Office for Outer Space Affairs that facilitates the sharing of asteroid observation data and coordinates the communication of impact warnings across national boundaries. Established formally in 2013 following recommendations from the UN Committee on the Peaceful Uses of Outer Space, IAWN connects observation facilities from dozens of countries through common data formats, communication protocols, and escalation thresholds. Its primary function is to ensure that asteroid discovery data and impact risk assessments flow reliably to all member institutions and that a standardized process exists for escalating warnings to national governmental authorities when assessments exceed defined risk thresholds. IAWN does not replace national monitoring programs, it integrates them. A positional measurement submitted by a small observatory in one country becomes part of the global orbital computation carried out at major computation centers elsewhere, and the warning products generated from that computation can reach governmental authorities across the network through a coordinated process. The network makes the global asteroid monitoring system more resilient by distributing observational capability and more comprehensive by incorporating data from instruments that no single national program could operate or fund. The Space Mission Planning Advisory Group, SMPAG, is a UN-affiliated body composed of space agency representatives that develops recommended protocols for the international response to a confirmed asteroid impact threat. SMPAG's focus is the question downstream of detection. Given that an asteroid has been confirmed on a collision course with Earth, how should the international community decide what to do, who should be responsible for the response, and how should the costs and risks of the deflection campaign be shared among nations? These governance questions have no direct precedent in international law. No treaty currently assigns authority or responsibility for deflection missions in the way that space law governs satellite operations or arms control treaties govern nuclear weapons. SMPAG works through consensus to develop the frameworks and decision processes that member agencies could apply if a genuine threat were confirmed. Its recommendations are not legally binding but represent the considered positions of the world's major space agencies on how planetary defense governance should be structured. Regular exercises and workshops allow member agencies to rehearse the decision-making process and identify gaps in authority, coordination mechanisms, and technical protocols before a real-world scenario requires applying them. NASA's Near-Earth Object Surveyor mission, NEO Surveyor, is a space-based infrared telescope approved for development and designed to substantially accelerate the survey of smaller near-Earth asteroids, particularly those approaching from sunward directions that ground-based telescopes cannot monitor. The mission will operate from the Sun-Earth L1 Lagrange point, approximately 1.5 million kilometers from Earth in the direction of the Sun, observing in two mid-infrared wavelength bands chosen to maximize detection sensitivity across the full range of asteroid surface compositions and albedos. Its position and wavelength coverage are specifically chosen to address the two most significant gaps in current survey capability: the solar blind spot that prevented detection of the Chelyabinsk impactor, and the albedo bias that causes ground-based optical surveys to undercount the dark carbonaceous asteroid population. Performance estimates based on the current mission design indicate that NEO Surveyor could discover the majority of remaining unknown near-Earth asteroids larger than 140 meters within its primary 5-year mission, substantially completing the mandate of the George E. Brown Act. In addition to discovery, the infrared photometry it produces for each detected object provides size and albedo estimates that optical surveys alone cannot supply, building a more physically complete characterization of the near-Earth population alongside the orbital data. The global Planetary Defense Survey system relies on a distributed network of follow-up observers, including professional astronomers at university and national observatories and amateur astronomers with adequately equipped backyard facilities, to provide the additional positional measurements needed to refine the orbital solutions of newly discovered near-Earth objects. Major survey telescopes are optimized for discovery, finding new objects efficiently across large areas of sky. They generally do not have sufficient allocated time to follow every newly discovered object, with the additional observations needed to reduce its orbital uncertainty to the level required for reliable impact assessment. The global follow-up network fills this function. When a newly discovered object is flagged as potentially hazardous based on its initial orbital uncertainty, observatories around the world receive alerts through channels maintained by the Minor Planet Center and Observing Coordination Services, and observers who are able to image the object submit their measurements to the global database. In some cases, amateur astronomers with modest instruments have provided the critical follow-up data that resolved an object's orbital uncertainty and removed it from impact risk tables. The Minor Planet Center validates and integrates these contributions alongside data from professional facilities, applying consistent quality criteria to measurements regardless of their origin. NASA, FEMA, and international partners conduct regular tabletop exercises, simulating asteroid impact scenarios to test decision-making procedures and identify gaps in planetary defense readiness. These exercises involve participants from the scientific, engineering, governmental, and emergency management communities working through a realistic impact scenario that evolves over a simulated timeline. Scenarios typically begin with a discovery announcement and proceed through stages of increasing orbital certainty and impact probability, forcing participants to work through decisions about when and how to communicate risk to the public, when to initiate mission planning, how to coordinate internationally, and in some cases how to plan for residual risk if deflection is only partially successful. The outcomes are documented and gaps in procedures, authority, or technical capability are used to drive improvements in protocols before the next exercise. Major international exercises in 2019 and 2021 were conducted in conjunction with planetary defense conferences, and the scenarios and findings were published for review by the broader community. These exercises serve the same function in planetary defense that disaster preparedness drills serve for other hazard domains, rehearsing the response before the scenario is real, identifying failures in the process under low-stakes conditions, and building the institutional familiarity with procedures that reduces error rates when those procedures must be applied under pressure. NASA's planetary defense mandate was established by the NASA Authorization Act of 2005, signed in the name of the late Congressman George E. Brown, Jr., which directed the agency to find and catalogue 90% of near-Earth objects larger than 140 meters in diameter. The broader federal government approach to near-Earth object hazards was formalized through the National Near-Earth Object Preparedness Strategy and Action Plan, first published by the White House Office of Science and Technology Policy in 2018 and updated in 2023. The strategy document assigned responsibilities for near-Earth object hazard preparedness across multiple federal departments: NASA, the Department of Defense, the Department of Homeland Security, and the State Department, reflecting the judgment that a confirmed impact threat would require a coordinated whole-of-government response that no single agency could manage independently. The 2023 update incorporated lessons from the DART mission, progress in survey capabilities, and advances in international coordination, while identifying remaining gaps in survey completeness, deflection technology readiness, and international governance that require continued investment. The Strategy and Action Plan framework represents the current basis of US government policy on planetary defense and provides the accountability structure within which NASA's Planetary Defense Coordination Office operates. NASA's Double Asteroid Redirection Test, DART, was the first spacecraft mission in history designed to test kinetic impactor deflection of an asteroid. The kinetic impactor concept is straightforward in principle. A spacecraft is directed to collide at high velocity with a threatening asteroid well before a predicted Earth encounter, transferring momentum that alters the asteroid's velocity by a small amount. Over the months or years between the deflection and the predicted encounter, this small velocity change accumulates into a positional displacement that can be large enough to ensure the asteroid misses Earth. DART was not a response to an actual threat. No asteroid was on a collision course with Earth when the mission was designed or flown. The mission's purpose was to demonstrate and measure the deflection method under controlled conditions, providing empirical data on momentum transfer efficiency that purely theoretical models could not supply. The specific questions the mission was designed to answer were whether a spacecraft could be reliably navigated to impact a small asteroid from the required direction, and whether the resulting orbital change was large enough to detect and consistent with the predictions of deflection models. DART targeted Dimorphos, a moonlet approximately 160 meters in diameter orbiting the larger asteroid Didymos. The binary configuration of the Didymos system was the primary reason it was selected as the test target. A change in Dimorphos's orbital period around Didymos, directly resulting from the momentum transfer of the spacecraft impact, could be measured precisely from Earth using standard photometric techniques. Measuring the much smaller velocity change imparted to Didymos's heliocentric orbit by the same event would have been extremely difficult with Earth-based instruments. The moonlet's 160-meter diameter places it within the size class that the George E. Brown Act survey mandate is designed to characterize, but that remains incompletely catalogued in the current near-Earth database. Selecting a target of this size was therefore both technically advantageous, providing a precision measurement mechanism, and scientifically relevant, demonstrating the kinetic impactor method against a body representative of the portion of the near-Earth population that presents a meaningful regional impact hazard if an object of this size were on an impact trajectory. DART launched on November 24, 2021 from Vandenberg Space Force Base in California aboard a SpaceX Falcon 9 rocket and traveled for approximately 11 months before reaching the Didymos system. The spacecraft used a solar electric ion propulsion system for trajectory corrections during the transit. In the final hours before impact, the onboard autonomous navigation system, designated Smart Nav, took control of terminal guidance, using real-time images from the onboard camera to identify and distinguish Dimorphos from the larger Didymos and steer the spacecraft toward the smaller body. Autonomous terminal navigation was necessary because the round-trip light travel time between Earth and the spacecraft at impact was over a minute, making real-time human control of the final approach geometry infeasible. Smart Nav was therefore also a technology demonstration element of the mission. The same type of autonomous approach and impact guidance system would be required by any future operational kinetic impactor mission, since the distances and timelines involved in asteroid deflection campaigns will generally preclude real-time human control of terminal approach maneuvers. DART impacted Dimorphos on September 26, 2022, at a velocity of approximately 6.1 kilometers per second. The spacecraft's final approach was captured in a sequence of images transmitted to Earth in the minutes before impact, showing Dimorphos's boulder-strewn surface in progressively greater detail as the distance closed. The final complete image was transmitted roughly 1 second before impact. The spacecraft's signal then ended, confirming the collision. Mission controllers at the Johns Hopkins Applied Physics Laboratory in Maryland confirmed the impact from the termination of the data stream. Post-impact analysis established that DART's navigation system guided the spacecraft to within approximately 17 meters of Dimorphos's geometric center, a navigational precision substantially better than pre-mission requirements. The impact was also observed by the Italian Space Agency's Lysia-Cube CubeSat, deployed from DART 15 days earlier, which captured images of the collision and the developing ejector plume from an external vantage during a brief flyby of the asteroid system. Photometric monitoring of the Didymos system by observatories worldwide following the DART impact established that Dimorphos's orbital period around Didymos had been reduced from 11 hours and 55 minutes to 11 hours and 23 minutes, a reduction of 32 minutes. The pre-mission success criterion required a period change of at least 73 seconds. The measured change exceeded this threshold by a factor of approximately 26. The larger-than-minimum deflection resulted primarily from the ejector enhancement effect. The DART impact excavated a substantial plume of surface material from Dimorphos, and the momentum carried by this ejected material, moving in the general direction of the impact, augmented the direct momentum transfer from the spacecraft. The ratio of total momentum transferred to asteroid momentum delivered by the spacecraft alone, the parameter beta, was estimated at approximately 2.2 to 4.9, indicating that the ejector contributed between 1 and 4 times the momentum of the spacecraft itself. The exact value depends on the mass and velocity distribution of the ejected material, which ESA's Hera mission is traveling to Dimorphos to characterize directly. The beta parameter is a key quantity for planning future deflection missions, since it determines the effective size of spacecraft, and hence the launch vehicle, required to achieve a specified deflection magnitude. The DART mission demonstrated for the first time that a spacecraft can deliberately and measurably alter the orbital velocity of a solar system body. Prior to DART, the kinetic impactor method had extensive theoretical support and broad endorsement within the planetary defense community as the most mature available deflection technique, but it had not been tested against an actual asteroid at any scale. The outcome of the DART experiment confirmed that the momentum transfer mechanism operates as predicted, that autonomous terminal navigation to a small asteroid is feasible with current technology, and that the ejector enhancement effect contributes to the deflection at the magnitude that models had suggested. It also validated the supporting measurement infrastructure, the global network of observatories that monitored the post-impact period change, demonstrating that changes in asteroid orbital parameters caused by a deflection event can be measured precisely enough to confirm success. The empirical data from DART is now being incorporated into deflection planning models, replacing theoretical estimates with measured values for several key parameters. This calibration improves the reliability of deflection outcome predictions for future missions designed against specific threatening objects. The DART impact produced a substantial ejector plume that was observed by ground-based and space-based observatories across multiple wavelengths in the hours, days, and weeks following the impact. Images from the Hubble Space Telescope and the James Webb Space Telescope showed the plume evolving from a narrow, bright jet immediately after impact into a broad, diffuse cloud and eventually a comet-like dust tail extending thousands of kilometers from the Didymos system, shaped by radiation pressure acting on fine particles. The tail remained detectable for several weeks. Analysis of the plume's brightness, color, particle size distribution, and rate of expansion provides information about Dimorphos's surface composition and internal structure that cannot be obtained from surface images alone. Observations of the ejector are being used to estimate the total ejected mass, constrain the grain size distribution of the ejected material, and infer properties of Dimorphos's surface layer. These data directly inform models of rubble pile asteroid response to kinetic impact, models that are applied to the design of future operational deflection missions against targets with similar physical characteristics. ESA's Hera mission, launched in October 2024, is en route to the Didymos system to conduct a detailed post-impact characterization of both bodies. Hera carries 2 CubeSats, Milani and Juventus, that will be deployed for close proximity investigations. Milani carries a visible camera and a hyperspectral imager for surface composition mapping. Juventus carries a low-frequency radar instrument to probe Dimorphos's interior structure and a gravimeter to measure its gravitational field. Together, Hera and its CubeSats will measure Dimorphos's mass, bulk density, shape, internal structure, and crater morphology at precision levels not achievable from Earth. This data will allow scientists to reconstruct the full physical picture of the DART impact. What Dimorphos was before the impact, what happened during it, and what physical mechanisms produced the measured orbital period change. The Hera measurements will calibrate the beta parameter, the ejector momentum enhancement factor, directly, replacing the current estimate derived from post-impact photometry with a value constrained by direct mass and structure measurements. This calibration is the primary legacy contribution of Hera to planetary defense engineering. It converts the DART result from a single demonstration data point into an anchored, physically understood benchmark applicable to the design of future deflection missions. DART carried a companion CubeSat designated LysiaCube, the light Italian CubeSat for imaging of asteroids, developed and operated by the Italian Space Agency. Deployed from DART 15 days before impact, LysiaCube flew past Dimorphos on a separate trajectory during the collision, equipped with 2 cameras that captured images of the impact site and the developing ejector plume from an external perspective that DART itself could not provide. LysiaCube's flyby of Dimorphos was brief. The CubeSat passed the asteroid within minutes of the impact, but the images it returned provided the first direct observational record of an asteroid surface immediately following a spacecraft impact and the first visual capture of the initial ejector development. The images showed a bright plume emerging from the impact site and illuminated surface features on the visible portion of Dimorphos. This data has been used to constrain estimates of ejector mass, direction, and particle composition, and provided an independent observational record complementary to the photometric period change measurements obtained by Earth-based observatories. The LysiaCube results demonstrated that CubeSats deployed as secondary payloads can serve as scientific observers during primary spacecraft terminal operations, extending observational coverage at incremental mission cost. The kinetic impactor deflection method requires substantial lead time to be effective because the orbital displacement achieved by a given velocity change grows linearly with the time between the deflection and the predicted encounter. A velocity change of 1 centimeter per second applied to an asteroid 10 years before a predicted impact produces a displacement of approximately 30,000 kilometers at the time of the encounter, roughly 5 times Earth's radius. The same velocity change applied 100 years before the encounter produces a displacement of approximately 300,000 kilometers, 50 times Earth's radius. This scaling means that the same spacecraft and impact velocity that would deflect an asteroid found decades in advance would be insufficient for one found only a few years before impact, which would require either a larger spacecraft, multiple impactors, or a different deflection method. The relationship between warning time and required mission capability is the central quantitative argument for early detection. Each year by which an asteroid is discovered earlier translates directly into reduced mission mass and complexity requirements for the deflection campaign. At sufficient lead time, deflection of most near-Earth asteroids in the hazardous size range is achievable with single spacecraft comparable in mass and cost to DART. At lead times of a few years, the same deflection may require spacecraft substantially larger than DART or multiple simultaneous impacts. Among the asteroid deflection methods studied beyond the kinetic impactor, the gravity tractor has been the subject of extensive analysis. A gravity tractor spacecraft would be placed in a hover position above the surface of a threatening asteroid, using continuous thrust to maintain altitude against the asteroid's gravitational attraction. The mutual gravitational force between the spacecraft and the asteroid, the spacecraft's small mass attracting the much larger asteroid by a tiny but persistent force, would gradually accelerate the asteroid in the direction of the spacecraft, which itself moves to lead the asteroid along the desired new trajectory. No contact with the asteroid would occur. The spacecraft's thrusters would be directed outward at an angle to prevent exhaust impingement on the asteroid's surface, which would produce a reaction force opposing the gravitational tug. In principle, the gravity tractor could be applied to any asteroid regardless of its surface composition, rotation state, or internal structure, including rubble piles that might respond unpredictably to a kinetic impact. In practice, the magnitude of the gravitational force between a spacecraft of practical mass and an asteroid of hundreds of meters in diameter is extremely small, requiring sustained operation over years to decades to accumulate a meaningful orbital displacement. The gravity tractor deflection concept requires no physical contact with the target asteroid and would function on objects of any composition or internal structure, but requires decades of lead time to produce a displacement sufficient to prevent an impact. The force exerted on the asteroid by a hovering spacecraft through mutual gravitational attraction is proportional to the spacecraft's mass divided by the square of the standoff distance. For spacecraft masses in the range that current launch vehicles could deliver, this force is on the order of fractions to single-digit newtons, far below what would be required to produce a significant velocity change over a period of years. Extended operation over a decade or more can accumulate into a sufficient displacement, but only if the threatening asteroid is identified with very long warning time, 30 years or more before the encounter. For scenarios with warning times of 5 to 15 years, the kinetic impactor achieves a larger velocity change in a shorter time and with a less operationally complex mission. The gravity tractor is therefore generally considered applicable to long lead scenarios where the primary considerations are minimizing disruption to the asteroid's physical integrity and achieving precise, controllable trajectory modification. Situations where the operational complexity of sustained proximity operations is an acceptable trade-off for the gentleness and controllability of the approach. Nuclear deflection, detonating a nuclear device near or on an asteroid's surface, has been studied as a potential last resort option for scenarios involving very large asteroids or insufficient warning time for conventional kinetic deflection. The concept does not involve pulverizing the asteroid, which would risk replacing one large impactor with multiple smaller ones on similar trajectories. Instead, a standoff detonation would deposit energy in a thin surface layer of the asteroid, vaporizing material that would be ejected at high velocity and providing propulsive recoil. This ablation-driven momentum transfer can, in principle, produce a velocity change orders of magnitude larger than a kinetic impactor of comparable launch mass, making it the only currently identified technique capable of deflecting very large asteroids or providing sufficient velocity change on timelines too short for conventional deflection. The primary barriers to implementing this option are legal and political rather than technical. The Outer Space Treaty of 1967 prohibits placing nuclear weapons in orbit or on celestial bodies, and extending an exception for planetary defense would require either treaty modification, a new international agreement, or a legal interpretation that has not yet been tested. These governance constraints are recognized in planetary defense planning as issues that would need to be resolved before the nuclear option could be operationalized. Some researchers have proposed using the Yarkovsky effect as the basis for slow deflection of asteroids identified with very long warning times. By altering the albedo or thermal emission properties of an asteroid's surface, for example by coating one face with a reflective material, the direction and magnitude of the Yarkovsky thermal recoil force can be changed. Over years and decades, the modified Yarkovsky acceleration would produce an orbital drift different from the natural drift, accumulating into a trajectory change sufficient to move the asteroid off an impact course given sufficient lead time. This method requires access to the asteroid's surface, a means of applying a persistent change in albedo over a substantial fraction of the surface area, and lead times on the order of decades. It has the advantage of producing no energetic disruption of the asteroid's structure and can be applied incrementally, with the accumulated effect monitored over time and the modification adjusted if necessary. The concept has been studied analytically but has not been tested on an actual asteroid. It is generally considered applicable only to small objects with very long warning times, scenarios where the kinetic impactor, applied once to reduce the need for monitoring and adjustment, would typically be simpler and more reliable. The Yarkovsky effect, orbital drift produced by the asymmetric thermal emission of a rotating asteroid, has been directly detected and measured for several hundred near-Earth asteroids, confirming that it operates at the theoretically predicted magnitude and must be incorporated into long-term orbital predictions for accurate impact probability assessment. The first direct detection was made in 2003 using radar ranging data for asteroid Golevka, which was found to have drifted approximately 15 kilometers from its purely gravitationally predicted position over a 12-year observation baseline. The magnitude of the drift was consistent with the theoretical Yarkovsky acceleration for an object of Golevka's estimated size, density, and thermal properties. Since that first detection, Yarkovsky accelerations have been measured for hundreds of near-Earth asteroids through combinations of radar range measurements, optical astrometry, and thermal modeling. For asteroid Apophis, the Yarkovsky drift rate is particularly significant because its direction and magnitude affect whether the 2029 close approach will carry the asteroid through gravitational keyholes that could lead to later impact scenarios. Accurately predicting Apophis's long-term trajectory requires knowledge of its Yarkovsky acceleration, which in turn requires precise measurements of its size, rotation state, and thermal properties, measurements that are among the primary objectives of observing campaigns planned for the 2029 flyby. The principle most widely agreed upon in planetary defense strategy is that warning time is the most critical determinant of response options. This principle has direct implications for survey investment, mission development timelines, and international coordination procedures. With decades of warning, a kinetic impactor mission using current technology is capable of deflecting most near-Earth asteroids in the hazardous size range. With a few years of warning, the same objective requires substantially larger mission resources and carries greater uncertainty. With months or weeks, deflection is not feasible for any object larger than a few tens of meters with current or near-term technology, and the response consists entirely of emergency management and civil protection. The relationship between warning time and response options is not linear. There are thresholds below which options that were available with slightly more lead time are foreclosed entirely. Survey investment is therefore the highest leverage component of the planetary defense system. It does not itself prevent impacts, but it preserves the option of prevention. Each year of additional warning time created by earlier discovery of a potentially threatening object is a year added to the response planning timeline that no mission can substitute for once it has been lost. China has announced plans to conduct an asteroid deflection test mission targeting near-Earth asteroid 2015 XF261, a program separate from the Tianwen-2 sample return mission directed at near-Earth asteroid Kamo-Oalawa. The Chinese deflection mission, described in general terms in Chinese space program publications, would demonstrate kinetic impactor capability against a different target from DART, providing an independently developed data point on momentum transfer efficiency under different conditions. The development of deflection capability by a second major space agency strengthens global planetary defense infrastructure by providing technological redundancy and creating the basis for potential collaborative multi-spacecraft missions against larger or more challenging targets. China's parallel development of sample return and deflection capabilities reflects an investment profile in near-Earth asteroid science and defense that is increasingly comparable to that of NASA and ESA. Coordination between Chinese and international planetary defense programs through established bodies, including IAWN and SMPAG, will be an important factor in the effectiveness of the global monitoring and response system as China's independent capabilities develop. The Vera C. Rubin Observatory on Cerro Pachon in Chile, operating the Legacy Survey of Space and Time, is expected to substantially expand the known near-Earth asteroid catalogue through its wide-field, deep, high-cadence imaging of the southern sky. The observatory's 8.4-meter Simonyi Survey telescope is coupled to the LSST camera, a 3.2 gigapixel mosaic detector capturing 9.6 square degrees per exposure, and is designed to photograph the entire accessible sky every 3 nights. The combination of aperture, detector size, and cadence provides sensitivity to objects substantially fainter than those detectable by current survey programs, extending the effective survey reach to smaller asteroids at greater distances. The Southern Hemisphere sky has historically received less near-Earth asteroid survey coverage than the Northern Hemisphere, where Catalina and Pan-STARRS operate. Rubin's southern location will address this imbalance, providing systematic coverage of sky regions that current surveys observe less frequently or less deeply. Population models suggest Rubin will roughly double the known near-Earth asteroid catalogue over its 10-year survey lifetime, with the greatest impact at the smaller size ranges currently least well characterized. Some researchers and commercial enterprises have proposed extracting mineral and water resources from near-Earth asteroids for use in space-based industries or for return to Earth. Metallic near-Earth asteroids contain iron and nickel in concentrations comparable to high-grade terrestrial ore bodies, along with platinum group metals, platinum, palladium, iridium, rhodium, osmium, and ruthenium, at concentrations substantially higher than those typically found in Earth's continental crust. The disparity reflects the fact that Earth's dense metallic elements largely migrated to the planet's core during early differentiation, depleting the crust, while undifferentiated metallic asteroids retained their original bulk composition.
Water ice in carbonaceous asteroids could in principle be electrolyzed in space to produce hydrogen and oxygen for use as propellant, reducing the cost of deep space missions that currently must launch propellant from Earth's surface. Whether asteroid resource extraction will prove technically and economically viable is uncertain. Early-stage commercial investment has been made in the concept, and the US Commercial Space Launch Competitiveness Act of 2015 established a legal framework recognizing the right of US citizens to own resources extracted from celestial bodies, though the broader international legal status of such activities remains under discussion. Planetary defense represents a historically novel capability. For the first time in the 4.6 billion-year history of the solar system, a species on one of its planets has developed the technical means to detect a natural impact hazard and act to prevent it. For the entirety of Earth's history before the late 20th century, asteroid impacts occurred without warning and without the possibility of response. The Chicxulub event, the late heavy bombardment, the Tunguska airburst, none of these was anticipated, and none could have been prevented by any technology available at the time. The system now in place, a global network of survey telescopes, automated detection and tracking software, international coordination bodies, impact risk computation centers, and a demonstrated deflection technology, represents a qualitative change in this situation. It is incomplete. Survey coverage of the smaller asteroid population remains partial. Deflection technology has been demonstrated once against a non-threatening target, and international governance frameworks are still developing. But the foundational elements are operational. Near-Earth asteroids are being discovered at thousands per year. Their orbits are being computed and monitored. Impact probabilities are being calculated and published in real time. And the DART mission demonstrated that when a spacecraft is directed to change the course of an asteroid, it works. The gap between the current state of planetary defense and a fully capable system is a matter of continued investment, additional surveys, and ongoing technological development, not a fundamental barrier. The near-Earth asteroid population that exists today has existed throughout Earth's history in approximately its current form, continuously replenished by objects migrating inward from the main belt. The impacts that shaped Earth's geological record and influenced the trajectory of life on this planet were not exceptional events in the context of solar system dynamics. They were the ordinary operation of a system that has been running for 4.6 billion years. What is different now is not the population or its behavior. What is different is that a species on this planet has built the instruments to see it. Telescopes distributed across multiple continents and operated from space photograph the sky systematically every clear night, looking for moving points of light that indicate something is there. Software compares those images and flags candidates. Astronomers compute orbits, calculate close approach distances, and assess impact probabilities. International networks share the data and cross-validate the results. And a spacecraft has flown to an asteroid and changed its course. The system is not complete. The survey of smaller objects remains partial. Deflection has been demonstrated once, under controlled conditions, against a non-threatening target. Governance frameworks are still being built, but these are known gaps being addressed through ongoing investment. The trajectory is toward more complete coverage, more precise characterization, and more options for response than exist today. Every near-Earth asteroid that has been discovered and catalogued is one fewer object in the inventory of the unknown. The catalogue will continue to grow. The watch continues every night that instruments are operating and skies are clear.